Hello, my name is Alejandro Gandara, and this is my Project 1 submission for Calvin Stewart's Mechanical Engineering Statics class. So, when tasked this project, we were asked to go out in the real world and find a example or a 3D static structure to analyze and find the equilibrium of. After much searching, I came across this hanging sign at one of my favorite local restaurants. I left the location below, and as it says, I highly recommend them because it's truly one of those hole in the walls inside of El Paso that has such beautiful atmosphere and amazing food. Here's a better perspective of the hanging sign that I found. And while looking at this perspective, um, I came to understand that it is a sign that is supported by two cables at sea. Oh, well, two cables at sea and what I would assume to be a bala socket and a constraint at D which prevents movement in the Y direction. I drew this example so you guys can understand what I'm basing my work off of and what it should look like. This is my free body diagram of the, the structure. These are my knowns and unknowns about the project. My knowns are the dimensions, weight, and coordinate of points. My unknowns are the cable tensions, reaction force vector at sea, and wind loads. Here are the coordinate of points. That is given to us by looking at the diagram that I provided, and the assumed weight of the sign, which is 65 pounds. Here's how I solved for the reaction at sea, which can be written as the formula that I gave above. I'm unsure if you guys could see this mouse actually, but I'm gonna do it anyways. So I made a little sections given here so you can follow me as I explain my work. At section 1, we're looking for the tension along EA. Here we're given the coordinate points and we solve that to find the position vector that allows us to find the magnitude of vector here. And having these given to us, it allows us to find the unit vector, which is the tension force, which we can use to find the moment of the tension force along C. Just gives us that. At 2, we follow the same process of getting the coordinate points and finding the position vector, which gives us the magnitude of the vector to find the tension force and the moment of tension FB along C. At 3, section 3 over here, we have a reaction at D, which is the force directed along the y-axis. So here is, since it's just in the y direction and it's 1, this allows us to find the unit vector and the magnitude of vector, which is same as how it is. We then are able to find the moment about C here. Then we go to section 4, which allows us to find the weight and the center of our gravity to find our moment about C for our force provided by the weight. Then here we find the equilibrium of our tensions and then at section 5 is a resultant couple about C. Firstly, we sum up all the moments about C and equating them in the I, J, and K components to 0 to solve and find our cable tensions and the force at dy, which are provided here. In C, we do something similar to section 5 because we have a resultant force about A. So we sum it up and solve using this equilibrium to find our tensions and force. Next is our wind load. I did a very basic wind load calculation. Here under wind pressure per square foot, you get a general idea of the pressure on a 1 by 1 foot section of a structure by using the formula provided here. And translating wind pressure to wind load must take account to the shape of the structure, which determines its drag coefficient, CD, a measure of wind resistance. Engineers have worked out standard CD values for different shapes. For example, a flat surface, which has a CD value of 2.0, which is a pure number with no units. So, with the pressure and drag data we found, we can find the wind load using this formula here. So, using this formula, we find the pounds per square foot of our sine, which is pretty massive. I used the highest recorded wind in El Paso to solve for this because you asked it under the most drastic, dire circumstances, which happens to be 86 miles per hour. Will it remain static? Personally, in my opinion, I don't believe that this sine will remain static because damaging winds are classified as those exceeding 50 to 60 miles per hour according to the National Severe Storm Laboratory. And for this project, to find the wind load, as I mentioned before, I used the highest recorded miles per hour of wind in El Paso, which is 86, which is severely close to wind speeds of 100 miles per hour that can produce a damaging path extending for hundreds of miles. People living in mobile homes that are anchored can easily get knocked down by wind speeds over 80 miles per hour. So I don't think this little janky sign is going to survive. That's personally, in my opinion, determined by the amount of pounds that are hitting this sign. It's ridiculous. Well, thank you for listening to my presentation and my project. These are the citations that I used to find some of my calculations and information. Thank you, and have a great day.